Okay, so you went in base n. Are you interested in seeing?
Okay.
If we see the pattern, and we can check if for base n, and we have to make n, let's say, greater than 3 or something.
Yeah.
But and we hope for when n equals 5, we get 1 out of 25. We hope for n equals 6, we get 1 out of
45.
45. Okay.
So for any n that we pick, it's always going to be 1 because you can't use 0 here.
Okay.
2 and 2 because you can use 1 and 0 here.
Yep.
All right.
And this is going to be n minus 1.
Then you have
n and n. So this is going to be.
Wait, hold on. Why would it be n minus 1?
Well,
Oh, good.
because
That's a very good question.
Well-
For the first digit, why is it n minus 1?
Wait, but n minus 1 would, if for base 5, that would be you could use 4.
Right. So for
0, 1, 2. But you couldn't use 0.
right. So we have what are our digits in base 5?
Well, you can use 0, 1, 2, 3, or 4.
0,
So-
0, 1, 2, 3, or 4.
Ah, I see.
But what's wrong with the first digit, or what's
You can't-
special about the
You
first?
can't use it.
Can't use
0.
0.
that's why it's n minus 1.
That's why it's n minus 1.
So then n and n.
So then we
So
get
then 4 over n minus 1 times n squared.
Aha.
So now we.
So there was an n squared in the pattern,
Yeah.
and you noticed that. What was special about 5 when n equals 5? You see what happens when n equals 5?
It's n minus. It's almost, because if you didn't have that minus 1, it would work.
Yeah, but what happens? You do have it. So what's n minus 1 when n is 5?
N minus 1 is 4.
So what happens to this fraction?
So it becomes 1 over 25.
It becomes 1 over 25. That n minus 1
Special for-
cancels with that 4.
Special for base 5.
And for 6, we get 5 times 36 with a 4 on the top. So what
Yeah.
is that? How does that simplify?
Well,
4 over 5 times
it's
36.
9 times 5.
Hey, so we got what we saw. Okay, so now if I asked you, what happens in, let's pick a big number. How about,
Maybe base 100.
okay, I wasn't going to go that high, but okay.
So 4
In base 100, how many numbers?
over 99 times 10,000.
Okay. Well, so you can just write it down, and you don't need to multiply that out.
And
It wouldn't be super hard, but you know.
Yeah.
Now you can just, now you know. So now you know how many 3-digit numbers in base n are just zeros and ones.
Yeah.
And it's amazing to me. It's kind of surprising to me that it is an unsolved problem. Nobody knows nobody knows two things.
Yeah.
If there's another number that's all ones and zeros in base 2, 3, 4, and 5, just 82,000 is where it seems to be very special. And the second thing nobody knows is if there's any number that would satisfy in base 6,
Yeah.
aside from 1.
aside from 1.
Yeah.
Right now, here's a slightly more advanced, but let's say we found that there were no more numbers in that 82,000 really was special. There was no numbers larger than 82,000 that were all zeros and ones in base 2, 3, 4, and 5.
Yeah.
What would that tell us about the 2, 3, 4, 5, 6 problem?
That it's an impossible problem
Why?
because 82,000 would be the last one.
It's the last one in base 2, 3, 4, and 5.
Yeah.
So why does that mean there could be none that satisfied it in base 6 too? Why couldn't there, if there were no more ones that satisfied it in base 2, 3, 4, and 5, only 82,000, why could there be no numbers that satisfied it in base 2, 3, 4, 5, and 6,
Aside from 1.
aside from 1?
Well,
This is a challenging question. So Richard Green walks into our living room and says, hey guys, I just proved it. There's no more numbers in base 2, 3, 4, and 5. 82,000 is the last one. It's special. No numbers bigger than that satisfy that property. Why would you know immediately that there were no numbers that satisfied it in 1, base 2, 3, 4, 5, and 6?
interesting. We figure that.
What do you think?
Well, Is there some sort of layover from base 5 to base 6 that would prevent it?
Well, I'll tell you one thing, 82,000 doesn't satisfy it in base 6.
Yeah, Richard Green said that in
Yeah, he
the
did.
post.
Well, that means, they're the ones that satisfied base 6 were all gone. They're all gone
Why?
because 82,000 was the last one in base 5, and if it didn't work in base 6, there would be no more ones except one.
Okay, that's pretty good explanation.
Yeah.
If you have a number that satisfies it for base 2, 3, 4, 5, and 6 would have to be bigger than 82,000.
Yeah.
But it would also satisfy it in base 2, 3, 4, and 5.
Yeah.
But we just learned
I don't know
from the
how many.
mythical Richard Green walking into our living room that there was no more numbers that satisfied in base 2,
Yeah.
3, 4, and 5.
Hmm.
So if you could prove that one theorem, that there were no more in base 2, 3, 4, and 5, then you
No.
could figure out there was none in base 2, 3, 4, 5, and 6.
Yeah.
So you'd be able to solve both problems.
You'd be able to solve both problems at the same time. Similarly, if you found one that satisfied it in base 6, that would be a counterexample to the prior one. That would mean there would have to be more in base 5. All right?
Yep.
All right. Good work, guys. That's a pretty fun unsolved problem.
Yeah.
Another unsolved problem that's accessible to kids.
Cool.